Hello! So last time we kind of did a little maximum problems. And we had a lot of cool problems. So let me do one more again so that we can kind of get everything acquainted. But we can minimize something, we can maximize something. So if we wanted to minimize something, we'd take a derivative and try to make it our critical number a minimum, right? So that's the essence of maximization. We're trying to find a maximum or minimum of a function. But we require like a secondary equation so we can relate the two things, because most of the time you're not going to have a simple, easy one variable function. So let's do something called related rates. So related rates is something that is relating rates. And I know that kind of sounds weird, but let's say we had a cone and we had some water and it was coming out of a cone, right? The volume of a cone is 1/3 pi r squared h. And I want to find the rate of change of volume with respect to time at a certain point. So at a certain point, how fast is the volume going out? How fast is the water draining? That's kind of what I want to wonder at a certain time. So what we do is we actually do implicit differentiation. So if we take a derivative of both sides, we get dv dt. We get a dv dt. And we get the power over 3, a constant out of the equation, right? Now we just have r squared times h. This is a product rule. So it's the first times the derivative of the second. Now remember how we did the derivative of y was dy dx. Because that's what it means, the derivative of y with respect to x. So the derivative of h is just dh dt. Okay, what about the first times the derivative of the second? Now don't put dr dt right away. See, this is r squared. So we actually do a little bit of a chain rule. And the chain rule is, well, we're going to take the derivative of our outside function, keep the inside, the r, the same, right? So the derivative of r squared is 2r. And then you multiply by the derivative of the inside, which is dr dt. And this is our derivative. So if we want to find out how fast the water is going out at a certain time, you have to know the radius at that time, the rate of change of the height of the cone at that time, the height at that time, and the rate of change of the radius at that time. It's a lot of information you have to know. And I can come up with those values and I can find dv dt. So related rates is kind of just differentiating, finding the rate that you're trying to relate. So let's do another one, a balloon. So if I had a balloon and its volume was expanding, now pretend this balloon is spherical. So, sorry. And and the volume was increasing. Well, the volume of a sphere is 4/3 pi r cubed. Now this is one variable. If we want to find how fast the radius is changing with respect to time, we're still going to have to take the derivative of both sides. So dv dt equals, well, we have the constant out here, times 3r squared, that's the derivative of r cubed, times dr dt. Hopefully you can see the pattern of these derivatives. So, but we have these 3's cancel out, so dv dt equals 4 pi r squared dr dt. And we want to solve for dr dt because we want to know what the rate of change of the radius with respect to time is. So we divide by that, so we get 1 over 4 pi r squared times dv dt equals dr dt. So now if we want to find out the rate of change of the radius with respect to time, it is 1 over pi, it's 1 over 4 pi. We need to know the radius at the time and the rate of change of volume of that time. So if I said the radius, so how fast is the radius expanding when the radius at that time is 2 centimeters and the rate of change of volume, how the volume is expanding at 10 centimeters per second. How fast is the radius expanding at that time? So we're not dr dt. Well, we can just plug in these values. So we get 1 over 4 pi times the radius squared times my rate of change of volume. Well, let's see, this is 416, so 10 over 60. So we get 5 over 8 pi is dr dt. And let's see. Okay. So if we plug in 2 into pi, we get 16, right? And this is 10. 10 over 16 is 5, right? This is how fast the radius is expanding, increasing at that time. It's kind of interesting. So, yeah. Centimeters per second. So that's related rates in a nutshell. I don't want to do more. So instead of making this video very short, I just don't want to. So I'll do an actual a bigger problem. That's better. So here's one of the better ones. I like these ones a lot. So let's solve this one. I encourage you to actually solve this one also. So there's a camera and it's watching this rocket. So it's kind of watching it. And at this moment, it's probably like right here. And the rocket is right here. It's going really fast. So the rocket is going up. And currently, it's 400 meters high. And it's moving at 2 per second. 20 meters per second. Now the distance between the rocket and the camera is 1,000 meters. So if you imagine if the rocket, if you're that far from the rocket, you don't really have to look that, your angle doesn't have to really change that high in order to see the rocket really high. If the rocket was this close, you're going to have to change really fast. So our answer is not going to be a very big answer. My question is, the angle. How fast does my angle have to move? How fast does my angle have to move for my camera to see the rocket? Or to keep track of the rocket? That's my question. This is a very interesting question, and I think so too. So, let's set up our problem. So, obviously we have 1,000 meters. This length is always constant, right? What about this one? I know we're at 400 meters, but is this length h constant? No, it's always going up because the height of the rocket is always going up. So the rate of change of the rocket with respect to time at that time was 20 meters per second, right? When h was what? 400 meters, right? So, oh well, it's kind of like a right triangle, right? And this is the angle that my camera is making. We want to know d theta dt, how fast my angle is moving with respect to time at that moment. We want to know how fast it has to go to keep up with the rocket. We want to find out that. So, okay. What would be this length? Because I'm sure we need it. So let's do this. The square root of 1,000 squared plus 400 squared is a big number. Sure is. So, holy smokes. What would this be? So, square root. So our answer, so the square root, I'll just put this down, the square root of 1,000 squared plus 400 squared is this 1, 2, 3, 4. This entire thing, this number 8. And I have to make it constant so I get an exact answer. And what is that? In meters, right? So that's a large amount. That's a big number of meters. So, how fast does my angle have to move to keep up with the rocket? That's going 20 meters per second, and at that time it's 400 meters. Well, what equation relates the height of the rocket and the angle at which I'm looking at the rocket? Well, can't we use the trig ratio? So, which one could be easier? Sine? Yeah, sine theta. So we can use opposite over hypotenuse. We can also use opposite over adjacent. I would love to use that one more. So tangent of my angle is opposite h over adjacent. Now let's take a derivative to find dh dt. So the derivative of tangent of theta is secant squared theta times the derivative of the inside, which is d theta dt. And the other one is 1 over 1000 times dh dt. So, okay. That's cool. So, let's solve for this d theta dt. So let's solve for it. So d theta dt equals 1000 times the secant squared theta, because we're dividing. And this is dh dt. So we have to know dh dt, and we have to know secant squared theta. Well, what's the secant theta? Well, the secant theta is 1 over the cosine theta. So it's hypotenuse over adjacent. And we know we have to square that. But we know dh dt. Wait, we know everything now. So d theta dt is 20 meters per second over 100 or 1000 times this big large number, hypotenuse over, this is meters square. So how fast does this have to go? So, well, that's the answer. And you know this is going to be a big number, or small number, because it's not a lot. So, let's figure this number out. So, this answer turns about 1/58 radians per second. 1/58 radians per second. Not that much. You have to move that much at all. That's the answer of a cool related rates question. Pretty cool. That's basically related rates. So again, related rates. We're relating our rates.